Hello everyone, my name is Kwon. I have been working at the Seoul National University for last about 30 years. In this video, I really appreciate this opportunity to introduce a new mechanical method, instrument indentation testing. Actually, instrument indentation testing is one of the most effective ways to evaluate mechanical properties done destructively in the field or to obtain nanomechanical data quantitatively. So the important features and advantages associated with the instrument indentation testing will be first described, and then some of the application examples will be shown. Finally, I would like to wrap up my talk with showing about standardization activities associated with IIT work. As you realize, safe assessment is indispensable procedures to prevent catastrophic failure of industrial structures and facilities such as power plant, nuclear facilities, oil refinery, and gas pipeline, so on, because breakdown of such large structures causes a lot of damage socially and economically. Thus, for long-term maintenance and affordable repairs, periodic mechanical diagnosis of operating components should be carried out before critical cracking is discovered. Especially, a change in mechanical properties of materials degrades significantly reliability and safety of structures and then reduce lifetime. In fact, most structures suffers from material degradations with time before cracking, which means the on-site mechanical property must be monitored. Therefore, there has been a strong need to evaluate on-site components non-destructively. Therefore, we have noticed the practical applicability of instrument indentation testings for in-field application. However, conventional testing, such as tensile testing or CTOD testing in laboratory, as you can see, this testing is destructive, which means it cannot be applied in field testing. Another limitation is this is large-scale specimens. We need special geometry of specimens for testings like this, so actually large-scale testing. So it cannot apply to small-scale testings such as thin film evaluation or weldment measurement. For these reasons, we have checked and noticed the practical applicability of instrument indentation testings for in-field testing or nanomechanical testing too. What is instrument indentation testing? You can imagine conventional hardness test in which hardness can be measured from the residual imprint size, which is resistance of a material to the penetration. However, in case of indentation testings, we can monitor indenting load and penetration depth of indenter into a material. So we can get loading, unloading, indentation curve. So as expected from this indentation load depth curve, we can come up with tensile strength fracture toughness, and residual stress in addition to hardness or lasting modulus. Therefore, instrument indentation testing is called different names, which reflects aspects of instrument indentation testing, like advanced indentation, continuous indentation, depth sensing indentation, or innovative indentation. And we call it this indentation load depth curve. Fingerprint of materials, because it provides very unique mechanical response of a target material without damaging materials or without preparing the specimen geometry. What is the characteristic of instrument indentation testing? Indentations no deeper than 100 micrometer is usually suggested to avoid indenting surface damage, because we need in-field testing done destructively. Actually, the mechanical response of indentations comes from local area close to indentation site. This local mapping capacity of instrument indentation testings make possible mapping of mechanical properties non-destructively, especially in the case of weldment, and in the nano-range evaluation too. For instance, when assessing the mechanical properties of weld metals, heat effect zone, and base metal. At each indentation site, we can get multiple data in terms of strain hardening exponent, yield strength, and ultimate strength, which means we can map mechanical property in terms of different mechanical behavior as a function of testing position. We call it mechanical mapping. In the right figure, this is grain boundary. Grain size is about 50 micrometer. That's why we need nano indentation testings. Nano indentation is performed across grain boundary. And then we can get nano hardness data as a function of distance. As you can see, a little increase in nano hardness, which reflects allowing segment regularizations near the grain boundary. Let me say instrument indentation testing is just simple and smart and selective. It is simple like a conventional hardening test. However, it is smart because we can get the depth curve. Finally, we end up with very different strength data or even residual stress. It looks like a fingerprint of material. And also by changing applied load, we can control the sampling size from macro to nano too. So we can say selective. So simple, smart, and selective. One of our important application examples using IIT is in-field testing as noticed. Because we can make indentations testings portable. So non-disruptive testings of on-site materials is possible. As you figure out, in the case of thin film evaluations or small sample testings, we can then use conventional testing, which requires certain large-scale specimens. So we can use nano indentations to obtain nanomechanical data in terms of strength, toughness, and residual stress. If you would like have more information on indentation testing procedures, you can refer to ASTM E54607. Title is Standard Practice for Instrument Indentation Testings, in which instrument indentation testing is defined as a mechanical test that measures the response of a material to the strain and strain of the sheath indenter. One of the biggest issues is how to determine the near contact area during the indentation, because observed contact depth H maximum is different from actual contact depth or area, because initially elastic diffraction and also pile up during the loading. So care should be taken in calculating contact area for applying the indentation. Indented geometry. We can group the indented geometries into two: spherical and sharp. Due to the geometry of a sharp indenter, angle between indenter at surface is not changed, which means surface strain during indentation is not changed. However, spherical indentations produce change in contact angle during the indentation. So, surface strain, especially near the indenter, continuously increase during the indentation loading. This continuous strains increase during the indenting loading can be used to get true stress strain curve over target materials.